Good morning. I trust we are all refreshed and enjoying our second day here together. And it's my turn to talk about another non-lang.net technology. I don't know about Lars. He evidently enjoyed himself. For my part, I am very happy to be here and talking about the fun problems of implementing managed runtimes, whether or not they run on Microsoft. I'm talking about the Java virtual machine. I've been doing Java for about a dozen years. One of Lars's VMs was Hotspot, which I still work on. I'm slow to move around. But what has happened in the last few years is we've discovered that Java is not the only language. Most of us knew that, but it took a while to actually get Java in a place where we knew it wouldn't die, and then we could begin to create new things on the platform that wouldn't crowd out the young seedling. Perhaps we could have done that 5 years earlier, but we're doing it now. And so we're looking for really fun languages to sprout up on the Java virtual machine as well. And that's what this talk is about. So there's a project called the Da Vinci Machine Project, more prosaically known by its common name, the Multi-Language VM, which is a little corner off of the Open JDK, which feeds clever ideas from the universities and other hackers into a patch set, which eventually goes, hopefully, if it's successful, into the main JDK 7. And a couple of large boli of code have already gone into JDK 7 from that source, including method handles. There was a recent commit. And what is a method handle? Well, it's what you think it is. There's nothing very special about it, but a good way to formulate it is it's an anonymous reference to a method, which other than that is callable like a named reference to a method. It's as similar as possible to a named reference to a method, except it happens to be accessed through a pointer capability instead of a linked name. The pointer capability is an object, because in the Java VM, everything except a handful of primitive types is an object. So a method handle is an object, but it's not an object that uses the object schema in any interesting way to talk about the signature of its call. So in fact, you can think of these things as being signature polymorphic, anonymous and signature polymorphic. You call it with, surprise, surprise, the name invoke, regardless of what the original method was named. You're quite familiar with this. .NET and C# had this a long time ago, something like this. I'll do the comparisons later. Why on the VM? For Java, can't you do everything with classes? Yes, you can do everything with classes, at least if you're doing things the Java way. But if you're going to do things the Scheme way, or the Smalltalk way, or the Ruby way, or the Python way, you need a little bit different access to the guts of the VM. The VM, of course, has method handles internally. It needs something to point to methods. So we need to reify them just enough so that we can call them. Why do we need to reify them? Well, turns out that the rules for method linkage in the JVM, which are designed for Java, are great for Java, but somehow those linkage rules don't fully apply to other languages. And we tried to make all the other languages adopt the Java linkage rules, but that didn't work. I'm lying, of course. So what we want to do is open up the linkage mechanisms that the JVM supports so that people can slot in their own call site linkage semantics. This is a very DLR-like thing to do. And in order to reify the subject of the linkage decisions, we needed method handles. The other alternatives don't scale well when you're doing lots and lots of small call sites. So there's a Vitruvian Duke equipped with a new set of toys, method handles. He's able to juggle them around and do new things with them. Now, we were, as I said, aiming not at method handles in this current push towards supporting dynamic languages. We were squarely aiming at dynamic call sites. And so some early designs used reflective thingies, Java lang reflect method to talk about the subject of a call site. So there'd be this sort of up call to the application. What are you linking this call site to? Oh, well, here is a reflective method that I want you to link the call site to, Mr. VM. And then the VM has to look at this big mass of symbolic and executional and permission information and pick out just the little bit that actually talks to the real underlying VM method. And also verify that the caller has access to it, and all sorts of stuff that is just too complicated. So we needed a more direct handle on the method. We went through it. By we, I mean my colleagues and I, which includes the JSR 292 committee, which includes Oracle and IBM and so forth. The first design with reflection just was ugly, and there was no way to see how to implement it cleanly across VMs. And of course, what we do in Java has to be implementable not just in one VM, but sort of a wide scheme of open-ended space of VMs. So it has to have reasonable, probably multiple implementation strategies. So we came to the conclusion that reflection was terrible, and then came back to the fundamental question: what does it look like when you make a call site in the JVM be user linkable while varying as little other properties as possible? Well, you have a up call, as I just described, but the result of the up call is to install an inline cache. Lars just described what an inline cache is, a pointer to what you think is going to be the target of the call, and it has to be, the target of the call has to be invocable basically at VM speeds. You don't want some kind of simulation overhead. You want the thing to hit the ground running when you call it, at least the second time you call it after you've linked it. You want it to, of course, not have loopholes in it. Like, that's the problem with C function pointers, right? They're too easy to cast to the wrong type. You want to be able to optimize with them just like you can optimize with named method calls. And you want there to be a certain amount of flexibility in what you put in that call site when you link it, in that inline cache. So the degrees of freedom that it turns out you need, and I think any of us in this room could do this analysis, you need, of course, to access any Java method. So if you're doing a call from Jython to a Java function, a Java method, you want to have that be a direct call. You want to be able to adjust minor type mismatches, because dynamic languages don't always get the types exactly right for their callees. That's okay. You want, as you sort of jump from one to the other, you want to be able to fix up argument types if necessary, box, unbox, cast, whatever. You want to do currying, because doing this without closures is a ridiculous exercise. I don't mean language level closures. I mean doing it without being able to combine some runtime management information with your target, if in fact your target is something in your language's runtime, like an interpreted method, which your runtime hasn't jitted to bytecodes yet. That's the way JRuby works. And you want to be able to do, like I said, inline caches, which involve a certain amount of fast, slow logic. Is it what it was last time and what I'm expecting? Yes, then directly go to the target. If not, then back off and do a relink step. Right? So you want, relinking is an important part of the mix. What's the contents of invoke dynamic call site? It's the basic symbolic information of the call, including the name that the caller thinks he's calling, which contains useful information if you're using it in a conventional way, but the VM doesn't care about the name. He just passes it through to the up call that relinks. You need, of course, static types at the VM level to maintain type integrity, and that's about all. There's some permissions issues. You need a call site to reify it as an object, which then the up call will manipulate. And no gratuitous mutability, please. The only mutable part of the call site is one word, one reference, which is your current target. And that is the method handle, which you can compare with .NET, where the contents of a call site is a sort of a collection of trees that you can edit as you go along, and then as I understand it, the JIT sort of compiles it down after you make your edits. Yes?
Contents of the call, the fundamental content of the call site in the DLR is a single delegate, which...
Right, okay. Jim says the contents are fundamentally a single delegate. There must be a side bag of expression trees that are cooked down into that delegate, right?
There are a bunch of things that are available for doing the various sorts of polymorphic inline caching things, but the fundamental, depending on how much you want to play, fundamentally all the call site holds on to is a delegate.
Okay.
The rest is extra information for languages that want it.
Good. Okay. It's more similar than I thought it was. All right. So here's Vitruvian Duke with his method handles, actually using them to create a little homuncular Duke that's actually doing work. And so he's dancing around playing with a Ruby and a Da Vinci helicopter. I have fun with the graphics. That was done for a T-shirt by a graphic artist who's much more talented than me. You should have seen my sketches, my original sketches. They were pretty lame. But anyway, so what's a method handle again? Where did my slide headers go? That slide should have been deleted. It's an anonymous method is something that is very like a named method. There's very little difference, except you have to invoke it with a ordinary with a boring name. Here's a sort of a snippet of the current definition of the root type of method handle. That impl thing needs to go away. But basically, it's extremely simple. It's got a type. That's it. That's all. There's a type token, which is a functional type descriptor. It's not a feature of the class. Neil is raising his hand because he doesn't understand that generic pseudocode up there. But what it means to say, I'll try and answer it and raise your hand again if I don't. What it means to say is there is implicitly an invoke call whose type depends on the runtime value of the type parameter, of the type attribute. In other words, each method handle has his own type that he knows about, and he will accept an invoke call of that type and only that type, statically bound at the call site to him. So you got to call him the right way, or he'll throw an exception. So it's not casting of classes. It's not the type isn't resident on a class. There's no schema of classes here. This is very monomorphic from a class perspective. It's a low-level piece of plumbing that has a token check to make sure your calling sequences match up. And there's no auto generation of wrappers or anything. You've got to get the calling sequence right. Does that answer your?
Yeah. Could you go to the previous slide?
Sure.
So there's two things. It's the second bullet and the fourth bullet. You say they can have any function type. The function types are not really. It doesn't know anything about the parameters or the return types, right? At runtime, the VM doesn't, or does it?
The question is whether what a function type is and whether a method handle knows his own function type. Function types are informatically the same as signatures viewed, JVM signatures viewed in the context of a call site. So that means they are a series of constrained classes and primitive types that are the parameters, and void or a return type. That's the return type. And these things are reflected, and you can ask about them. You can ask a method handle for his type, and you can ask the type for its return type and for its nth argument type.
So if there's a concept of function type in the VM, are they covariant on return types and contravariant on argument types?
They are completely invariant. This is very low-level plumbing. If you want to do covariance and contravariance in your language, your call sites have to express that in terms of type adaptation, which I'll get to. But they're invariant is the short answer.
And what do you mean by signature polymorphic?
By signature polymorphic, I mean that method handles viewed as a type have a free variable in them, which cannot be expressed in the Java generics, for example. It's a new kind of free variable, which ranges over all possible JVM signatures. And that's the thing. Each individual instance binds that variable to one signature, and that's the only invoke he'll take. And the JVM makes sure he only takes those kinds of invokes and throws a low-level null pointer type exception, not exactly null pointer, but a low-level cast.
Just if I have something that's a method handle variable, I can assign to it a method handle of any arguments and return types.
That's right. That's right.
Which means you really do have covariance, heterovariance, because it's completely variant.
Well, it's there's a top type which wildcards the signatures. Here's the low-level structure in its minimals. It's, the gray rectangle is a call to a method handle that happens to be calling it with a single int argument and expecting an int return, and that's encoded in the signature at the call site. And therefore, the method handle himself has to accept exactly that signature type. He'll throw an exception if you hand the wrong kind of method handle to it. So it's up to you to match. Basically, it's up to you to make sure your program links. That's what it amounts to. I mean, this is the restriction that Java programs work under already. You can't just link a thing, two different signatures together where the caller and the callee disagree about signatures. And method handles simply enforce that same invariant. There's a little bit of trampoline code, usually just a few instructions called a VM entry, which make up any method handle peculiarities between the caller and the callee. And then there's a managed pointer on at least one managed pointer on every method handle that points often to a low-level inscrutable VM structure, which Java will never see. Let's do some comparisons. Is it like reflection? There's no boxing. As you can see, with the signature polymorphism, there's no need to boil everything down to a single one-size-fits-all signature. So there's no wrapping of any sort going on. Question, Lars?
What's the performance of megamorphic call sites in this case here? So is there a way of speeding up the megamorphic call
What's the performance of megamorphic call sites? That's kind of up to the dynamic language implementer, but method handles give you at least a way of emulating every single of the pre-existing invoke instructions. So you can, for example, have a method handle which will be a faithful invoke interface. So you can use that to bottom out to a megamorphic guy. Probably what you want to use, if you're tuning this thing right, is you want to use bound method handles or static methods that don't involve any dispatch at all. So it's basically a jump. But if you need to back off, one way you can back off is to an interface call, and then you have to then it's up to you to create the schema of interface callees at that megamorphic point. So that's one way to do it. Another way to do it would be method combinators, which you'll see in a second, with decision trees. Not reflection. I think there's a bunch of difficult aspects of reflection which come from, thank you. Was that 10 or 20? Thank you. Reflection is intended to emulate a statically bound call at the call site which is making the reflective call, which means that the linkage checks, including the access checks, are performed. Oh, great. Should have done that myself. iPhone, yeah. A reflective call performs an access check on every call, which means, but there's a mismatch because you can have a different reflective method at every time you execute one call site. So you can't do the access checks just once easily in a reflective call. I don't know if it's the same in .NET, but it's a difficult it's a difficulty with the JVM. So in fact, what we do is we get away from that model with method handles. We perform access checks on creation and not on invocation. So invocation is full speed. And we don't bundle a whole bunch of symbol table information up with the method handle. It's totally opaque, and in fact, the spec is very vague about which kind of method handle you get from which kind of method handle constructor. It's up to the VM to create method handles however they want. There's no class structure to them that's interesting to the user. Oh, and reflective methods can't be curried, but method handles can, and that's crucial, of course. Inner classes. The difference from inner classes is that they don't have a lot of intentionality on them. It's just, you call them, regardless of what fancy thing your method handle is doing, you always call it by saying invoke. That's a very function pointer style of pattern. With adapter classes, you have creative names, at least for the methods. do this thing to my thread computation. They, like inner classes, however, method handles are small and lightweight and can be invoked quickly and basically introduce an indirection into your call path. And in fact, with invoke dynamic, the indirection can be folded into the call side and inlined, unlike inner classes. Like delegates, yeah, they are like delegates. There's that magic linkage to a VM internal method. In hotspot, and probably most VMs nowadays, most Java VMs, everything gets managed. Even the internal pointers are managed. So in hotspot, for example, you can load lots of classes and then garbage collect them. And a method handle can have a managed pointer to something in the middle of a loaded class and use that method. And then when he drops it, then that class can get garbage collected. So there's the magic internal pointer of the method handle is managed like most everything else. Big difference from delegates is they are the type system is, as I described, based on structural tokens, and so there's no nominalism at all in the typing of method handles. A significant weakness relative to delegates at present is we don't have an LDC method handle opcode. There's no like load constant function opcode, which I think we need, but that's a persuasion job on all the JVM vendors. Here's a simple direct method handle where the magic pointer points directly, as I said, to a method. And so the call just goes straight through. There's nothing to it. Direct method handles, a matter of terminology, can include virtual semantics or interface semantics. They're typically used to go straight to static linked things, but you can roll in a vtable indirection into them too. That's one of the subspecies of direct method handles. So basically, it's an emulation of one of the invoke instructions. Can be bound or curried. Here's an example of a bound method handle. You'll notice there's a node structure here where the bound guy has a pointer off to some argument, which could be an int or could be a reference, and then he has a target of a direct method handle, which then goes to a class. And you can see the bolded parts in the code show the difference of adding the extra curried argument, which in this case is an int, but usually it's more interesting than an int. Those two nodes, in some cases, are fused, but that's an internal optimization in the VM. For exposition, it's easier to see them separated. You can also have adapters which make up small differences in calling sequence. So if you're passing a char but you're expecting an int, then usually you can just jump through. But if you're passing an int and expecting a char, you might have to strip some high bits. So there's some. The VM knows how to clean up a few of those small messes kind of natively in its own guts, and those cleanup steps are all tail recursive. So you sort of jump through your linear method handle node structure, and you get to the receiver having cleaned up your calling sequence, and you're done. Invoke dynamic call site has that mutable method handle pointer, which is diagrammed here, one in a linked and one in an unlinked state. And I think there's no real surprise here, except you may be looking at the pseudocode and look at the method name. Remember, I told you they were uninterpreted by the VM. So I made one method name on the unlinked site especially ugly, just to show you that they're arbitrary strings. There are like a half dozen characters that you're not allowed to put in these, but every other Unicode point is allowed, and there's some simple mangling rules to take care of those half dozen that you're not allowed to utter. So basically, it's an arbitrary string. You can put a whole JavaScript program in that method name, and if your linker expects it, he can like generate a method handle complex that will execute that program. I mean, that's one thing you can do. It's more likely you're going to have a naming scheme for each language with a URL-like system of prefixes, and so we reserve colon to structure the names that way, so that different components of the Met Object Protocol don't get in each other's way. Here's an inline cache. There's a complex of method handles. There's a guard combinator which points to a predicate and also a target and a fallback. And the fallback is a bound method handle that's bound to some runtime management information. So if he ever gets called, he knows how to relink his call site. Notice that the argument of the bound method handle points back to the call site, which will be reified. And so the bound guy can then, is that a 5-minute warning? Thank you. The bound guy can then relink the call site. But the fast path is straight through after doing the check. And the important thing is, from the pink root there, the JIT can inline. This is all immutable structure, except for the mutability of the pink triangle. So everything else can be inlined into code in the call site. And then if something changes, if the target gets changed, then you can throw away the code and regenerate it if you want. I just said that. So I have some cheesy animations that show how call sites work. This is just a vtable, which you all know how it works. Step 1, load object header. Step 2, load vtable entry. Step 3, jump. Compare that with a method handle call. The dotted arrows are dependent loads, so those determine the speed of your transition. And so first you do 2 independent loads. You check the method type, and you also get the little trampoline stubby guy. Next step is you load the actual target method from the method handle, and then you execute. So it's about another memory indirection. And as I said before, that can be inlined in invoke dynamic. Bound method handle details are just slightly more complicated. You of course have to load and stack the target object, and then execute. Well, that's how you check integrity of. You maintain the integrity of the VM by making sure that whenever you jump through a method handle, the caller's intention about the exact linkage type agrees exactly with the called method handle's type field.
That's what you mean when you said they're invariant.
They're invariant. Yeah, it's a token check. So there's other stuff cooking there, which I don't have time to tell you about. But it's in the DaVinci Machine Project Patch repository. People are using this stuff. The committee is committeeing. Java 1, there's a Java 1 preview for this, and I guess I just have to leave you with a teaser. But there's a new project which just is starting to produce code on interface injection, which is a way of retrofitting system classes to new meta-object protocols. This slide's for you, Eric. The pun about needling. But basically, when you have a specially marked injectable interface meeting up with a system class like string for the first time, here's groovy meta-object protocol. Here's string. They meet. Now I dance. They meet for the first time, and then groovy meta-object protocol has an opportunity to inject into string a tuple of method handles actually, that implement that protocol. So then, therefore, forever after, strings are equipped with a groovy meta-object protocol, even though the designer of the string never heard of such a thing. So that's interface injection in a nutshell. There are fun details about that, but I posted my slides on my blog. You can see the fun diagrams for interfaces at the end. Questions?